Good morning, students. As a continuation of last session, today we begin our discussion on quantum technologies, which is a field that bridges physics, computing, and engineering. Before going to start today's session, quickly recap last session in which we discussed about the conceptual difference between the classical mechanics and quantum mechanics. But classical mechanics developed by the Newtons deals with the large scale macroscopic objects like a car moving or a ball falling under gravity. Whereas in the case of quantum mechanics, which explains behavior of extremely small particles like electrons, atoms, and photons. Now, for example, if you throw a cricket ball, I can predict exactly where it will be land. But if I study an electron inside an atom, I can only say where it is likely to be, not exactly where. That is the key difference of certainty and probability. In case of classical mechanics, both position and momentum of an object can be measured exactly at the same time. For example, we can track position and velocity of a car using GPS and radar. That means no uncertainty at all. But the equations, if you see, that belongs to energy, which is a sum of kinetic energy and potential energy, are deterministic. That means for a given initial state, you can compute future state very precisely. For example, the projectile motion under gravity. Whereas, according to Planck's quantum theory, the energy of emitted or observed energy in a discrete packets called quantas. Each quanta has a energy that is E is equal to h nu, where h is the Planck's constant. However, if you put h is equal to 0, we can regain the classical mechanics. For example, think of it like a staircase where you can only stand on specific steps, not between them. Similarly, electrons in atoms can only occupy certain energy levels, not in between space. What I mean to say is, in which the energy is quantized, is not a continuous. Energy can only change by well-defined amounts. That means not a continuous. But come to the quantum mechanics postulates. In case of quantum mechanics, every physical system is described by a wave function, denoted by psi. This wave function contains all possible information about the system, like position, momentum, and energy. The evaluation of the system or behavior of the system is governed by Schrödinger equation, unlike Newton's equation in classical mechanics. In case of microscopic world, let us see how to describe a system as a Schrödinger equation, in which the wave function psi will describe the whole status of the system. But to understand the concept of Schrödinger equation to describe any system, let us consider a particle in a box. Consider a particle is trapped in a one-dimensional box. It can have only certain allowed energy levels. Like if you see here, that means outside the box, the energy is 0. Inside the box, the potential energy is equal to 0. If you solve by applying the potential energy which is depending upon x, we will get the energy expression is equal to h square by 8m L square, L square, where n is the integer. That means the energy is continuous. For n is equal to 1, it is a certain energy level. For n is equal to 2, it is a certain energy level. N is equal to a certain energy level, and so on. For example, let us consider an example. Think of guitar string. Only specific vibration frequencies produce at the musical notes. But the particles in a box also behave similarity. That means only standing waves fit inside the box. That reveals that is discrete energy levels of a system. Now let us compare classical mechanics with quantum mechanics in terms of determinism and probability. In classical mechanics, if the feature is deterministic. For example, for a given system, if you know initial conditions like of a planet, its future path can be predicted with certainty. Whereas in the case of quantum mechanics, only probabilities of outcomes can be calculated. For example, in case of radioactive decay, we cannot say where the single atom will be decayed. Only probability that will be within a certain time. That means even if you know the wave function, one can only predict the probability distribution of a measurement outcome, not exact values, like classical mechanics. Let us try to describe both the classical mechanics and the quantum mechanics mathematically. In classical mechanics, we'll use the Hamiltonian equations, whereas in quantum mechanics we use the Schrodinger equation. The Hamiltonian operator H defines the total energy of a system, whereas in case of quantum mechanics, the psi function will describe the whole properties of the system. But let's compare both in terms of phase, that means phase space and Hilbert space. In classical mechanics, we describe the particles in a phase space, that means position and momentum. It allows visualization of the trajectories in phase space, that means the position and momentum. Whereas in quantum mechanics, the system is described in a Hilbert space, the space that means space of wave function. For example, phase space like a map with x and p axis, whereas the Hilbert space is represents all possible wave functions of a system. That means to understand the behavior of the any system. Let us come to the uncertainty principle. According to this, we cannot simultaneously know the particles' exact position momentum. There is always uncertainty governed by this. For a given that the delta x dot delta p greater than or equal to s plus by 2. This deviation arises due to the wave-like nature of a particle. One can say the fundamental limit on a measurement of accuracy in the case of quantum mechanics. However, in case of classical mechanics, there is no such limitation. As you discussed, the exact position of momentum is measurable. For example, if you try to pinpoint the electron's position precisely with high energy photon, we disturb its momentum. That means the measurement itself changes the system behavior or system status. This is summary of classical mechanics and quantum mechanics, which is category like in case of particles, what are the parameters are going to consider, like mass, position, and velocity. Which type of behavior is supposed to study, that is momentum collisions. On the other hand, in case of quantum mechanics, deals with waves. The properties will consider is wavelength and frequency. The behavior of waves can be understood by means of by studying diffraction and interference. Based on the discussion, let me conclude what is the classical mechanics that gives the accurate measurement of macroscopic systems, whereas in case of quantum mechanics is essential for atomic and microscopic system. However, as I discussed in session 1, the classical mechanics is the extension of quantum mechanics. Simply by putting h is equal to 0, h cross is equal to 0, the quantum mechanics becomes classical mechanics. That means it's a continuation of or extension of quantum mechanics. Now let us see what is the quantum states, how it connected with measurement. When you see the measure of a quantum system, as per the definition of superposition status, it collapses from superposition of states into one definite state. This leads to there is famous observer effect, which causes the measurement changes the reality itself. That means the measurement challenges like observer effect and decoherence must be navigated to define applications of quantum mechanics. But it's not static. It is the status is depending upon the or influenced by the observer role. Let's recall the concept that is concept of nature of observation. According to superposition principle, before measurement, a system can exist multiple states at once. Once it is measured, the system collapses into a definite state. For example, consider a cat in a box that is popular known as Schrodinger's cat. The cat can both alive and dead until observed. That means observation collapses into a definite state. That means alive or dead. Similarly, if you consider the double slit experiment, electrons from interference pattern when unobserved, but act like a particles when you measured. That means the observations defines outcome. The key idea behind it is the measurement does not just reveal the state, it alters the. Let us go to the next topic. That is overview of quantum systems. All the quantum technologies are built on a basic systems which is composed of electrons, protons, photons, and atoms. Let us see one by one in very brief. Electrons carries the charge which is negative and exhibits wave particle duality, which is responsible for electric current and chemical bonding for any system. The quantum behavior of electron is described by wave functions and probability distributions. For example, the working of your mobile phone processor depends upon entirely depends upon a controlled electron movement. We can describe the behavior of the electron by knowing the wave function and the probability distributions. Next come to the photons. This is fundamental particles of light, which is massless and chargeless, but full of energy. It exhibits wave particle duality and carries energy and momentum. But the behavior of this light can be understood by studying interference, diffraction, and entanglement. If you consider real-time example where you are going to use this in the case of quantum technologies, fiber optic communication and quantum cryptography rely on photons, which carries the information very securely. Next, come to the atoms. It consists of electrons, protons, and neutrons. Atoms have a discrete energy levels. That means electron jumps between levels. They emit or absorb the photons. We can understand the quantum behavior by studying atomic spectra and superposition of states. Consider real-time examples is laser, where laser works because of atomic energy level transition, where electrons jumps from high energy level to the low energy level. The emission of light takes place. Let me summarize all the particles like electron, photon, and atom in terms of type, key quantum features and applications. Consider the electron is concerned, it is a matter composed of matter. Quantum features, discrete energy, spin tunneling, exclusive principle, application point of view is a quantum computing. In case of photon, where you can use it in laser and quantum optics. Atom is a composition of electron, proton, and neutron. Because of the discrete energy levels, the quantum transition and atomic spectra, we can build a atomic clocks by using atoms. Let us try to understand what is the concept of quantum quantization and energy levels. In a quantum systems, energy comes from the discrete levels, means it's not a continuous values. For example, the hydrogen atom in which the electrons occupy only specific orbits defined by the quantum numbers. As we came across last slides, that E is equal to h square by 8 into ml n square when is the integer value. But the transition between these levels must produce a unique spectral lines. We see that is depending upon the energy, that is E is equal to h nu based on energy levels, but the frequency corresponding wavelength will vary. However, no electron exists between the levels. Each level corresponds to quantum number. But the concept reveals the energy is quantized. The electrons and atom occupies discrete energy levels. See, when electron jumps from high energy level to high energy level from low energy level, it absorbs energy. On the other hand, when it falls from high energy level to low energy level, the emission takes place like an LED or laser. But it reveals the concept of quantization and how the energy levels are discrete, how we can make use the discrete levels concept, but to build the systems like lasers, like photo detectors, etc. Now let us jump into the importance of quantum. Why quantum mechanics playing a vital role? As of today, you have to keep on talking about quantum. Why quantum? What is the need of study the quantum? Here you're going to see the importance of quantum in terms of scientifically, technologically, and statistically. But quantum mechanics explains a phenomena that classical phenomena cannot do. It is a foundation of technologies like lasers, semiconductors, and MRI scanners. Let us see what is the significance of quantum in terms of scientific. It is able to describe subatomic and subatomic particles and behavior of the bonding and electron orbitals. We can build lasers, semiconductors, and MRI machines. If you consider what are the emerging technologies is considered, these are the upcoming technologies like quantum computing, which supports speed and parallelism, and quantum communication is unbreakable encryption, which gives high security. As quantum sensors, ultra precise measurement, where you can use that as gravity in terms of time. But let us see the quantum computers, where you can use the qubits instead of bits. The application is concerned, which is used to solve the complex problems in seconds. For example, Google's 53 qubit system performed a task in 200 seconds. That would take a classical supercomputer take 10,000 years. Just imagine what is the beauty of quantum computing, what is the need of studying quantum computing. Whereas the quantum communication is concerned, which is suitable for secure data transmission using quantum cryptography, ensures as I mentioned, unbreakable encryption using quantum principles. For example, if you consider recent update in China, China's MIQ's satellite used a quantum key distribution, that is QKD, to transmit secret codes between the cities very securely. Next, come to the quantum sensing point of view, which supports extremely measurement of time, gravity, and magnetic fields. That means able to measure extremely small changes in magnetic and gravitational fields. Using this concept, we can go with quantum magnetometers, which can detect brain activity. We can say which leads a breakthrough in case of early diagnosis of diseases. It's very useful in magnetic image like MRI scans, all this in the medical field. However, of course, quantum materials, new phase of matter like new materials is supposed to like new superconductors. That means the conductivity properties of material goes on changing when you come down the size of the particles like in nanostates. Next, let us see what is the strategic and geopolitical significance. What is the need of focusing on the quantum technologies? If I say, is a quantum race among the nations as major countries like USA, China, European, India investing billions of amounts but towards development of quantum systems by considering the national security edge. Whereas if you see the budget invested by the various countries, the quantum industry is going expected to be a more than 1 trillion by 2040, which creates a more and more jobs in areas of quantum engineers, physicists, and software developers. Of course, no doubt, it creates new markets in case of quantum cloud services and quantum internet. Next, let us come to the what is the national global importance of various quantum technologies, which are to discuss like quantum computing, quantum communication, and quantum sensing. Come to the quantum computing is concerned, where you discussed to solve the problems that in classical computers that cannot be handled efficiently in terms of time. As per Q features is concerned, it uses the qubits instead of classical bits. It supports the parallelism. Ultimately, it leads the saving of time. As you came across as Google's 53, able to solve the problem with 200 seconds, where a classical computer took 10,000 seconds. Just imagine how fast it is. Come to the applications where you can use the cryptography, drug discovery, material science, and AI acceleration. But similarly, for quantum communication, which ensures the transfer of information using quantum mechanics, in which we're going to use the QKD, which supports sharing of information very securely. We can make use of this concept in secure communication networks. This will be one of the key technology in quantum internet in future. Similarly, as I mentioned, sensing will plays the major role, especially in the case of medical. As the quantum sensing measure the extremely small changes in the magnetic and gravitational fields, which plays the vital role in the case of medical imaging, early detection of lesions by using a superposition, which increases sensitivity and entanglement for correlated measurements and increase the precision. This is one of the key areas in addition to medical imaging is navigation, geology, where it is useful to study the fundamental physics. That is the importance of quantum sensing. Let's have a look on the summary. What are the different domains in the quantum technologies? What are the features we have? Where you can use that? What are the different types of applications we have? Like in quantum computing, features are superposition and entanglement, drug discovery, cryptography, and optimization. Whereas quantum communications, which are secure transmission and supports QKD. It may be a one upcoming technology, like in case of internet and secure military applications. There in the case of quantum sensing, it's ultra precision measurement. We can use for GPS, geophysics, and MRI. Now, however, we discussed the quantum technologies in different ways, like quantum computers process data, quantum communication links them securely, and quantum sensor help calibrates both. This only forming the overall integrated system. Even though we study individually, that means all together will be a ecosystem for future applications. That means that together they drive the quantum technological revolution, not individually. We are supposed to integrate all of them in the same system, then only that becomes very useful. That means quantum computing, quantum communication, and sensing all together you have to keep in a single system. Now let us see, by considering all these aspects, let's try to find what is the present status of quantum computing by various nations. That means what is the initiatives taken by the different nations in the field of quantum technology on research, collaborative and strategic advancements to ensure the competitive advantage and technological importance. Let us see what is the present status of quantum technologies in India. In India, it is a national quantum mission with 6,000 crores budget, focusing on the quantum technologies like computing, communication, sensing, and materials. The key goals behind it is to make a intermediate scale quantum computers, communication networks, magnetometers, atomic clocks, and quantum sensors, and four T hubs is to support academic and R&D institutions and collaborate with industry to face the challenges posed by the present technology, as all you are new to the this quantum technologies. This is the initiative taken by the Indian government. Now, similarly, European Union having a budget around 1 billion, which is started in 2018. Some focusing on the quantum computing platforms, quantum simulations, and sensors and communication networks. More or less, the objectives of the every nation is same. Let us go for the US. Again, we start with the 2018 National Quantum Initiative with 1.2 billion years. Now focusing on the quantum information science, quantum networking, quantum algorithms, and hardware required to supports by the quantum technologies. However, among the all countries, China is started as earlier, that is in 2016 itself, with as of today with the largest budget. In case of quantum communications and computing, of course, the milestone is the message satellite, the first quantum communication satellite, world's largest quantum communication network, that is around 2000 kilometers we have. Prototype computer, Jiangjiang with quantum supremacy. But the strategic aim is they are going to incorporate these technologies in the military for secure communications and all other fields like medical imaging and normal communication and all these things. But this is a comparison snapshot of each country. Of course, I try to compare only major countries. But by seeing this, the quantum mechanics, the quantum technologies is promising by requiring interdisciplinary efforts, but to inviting all to explore this innovative field. But it is the foundation for next technologies and revolution. Understanding these principles empower empower engineers and scientists to shape the future from quantum computers to quantum internet. By considering the quantum technologies like quantum computing, communication, and sensing, by collaborating with physics, engineering, computer science, and mathematics, all together to explore a new system like ecosystem by combining all this to transform the quantum computers to quantum internet. Next session will deal with unit 2, that is theoretical structure of quantum information and systems. Thank you for your patience.